Good afternoon everyone, and thanks to you all for joining us today's webinar, which is the Fundamentals of Masonry Arch Bridge Analysis with LimitState Ring. I'm Tom Pritchard, I'm the host for today, and shortly I'll be passing you over to our speaker, who is Professor Matthew Gilbert. He's the LimitState Ring Product Manager. This webinar is going to provide you with an overview of Masonry Arch Bridge Analysis using LimitState Ring, and we'll cover some of the main issues that engineers may encounter when undertaking an assessment and how these will be accounted for using the software. The main part of the webinar will run for about 35 minutes, and we'll have a little time at the end for questions, which you can post at any time using the question functionality that should be present in the webinar interface in front of you. We'll try to answer as much as we can in the time available, but this isn't always possible. However, we will respond to anything that we don't get to during the webinar within the next day or so. So without further ado, I'd like to introduce you to our speaker today, who is Professor Matthew Gilbert.
Thanks very much, Tom, and thanks very much to everyone for joining us today for the webinar. Okay, so what I'm going to do is go through a number of fairly basic topics. First of all, I'll have a look at aspects related to masonry arch bridges and their analysis. I'll then move on to look at how we can do masonry arch bridge analysis using LimitState Ring, and also a little bit about how the software works and how it's been validated. Then, because it's a relatively short webinar, I'll just look at one example analysis. It'll be a twin-span highway bridge in the UK, and then wrap up with some conclusions. Okay, before I get into the webinar proper, just a few words about LimitState. It's actually a company spun up from the University of Sheffield in 2006, so we've recently celebrated our 10th anniversary. The aim of the company is to commercialize academic research, providing engineers with powerful software, primarily, although now not exclusively, for the limit state analysis and design. And key thing that we're able to do is take advantage of state-of-the-art algorithms and optimization technology that have been developed in the university. As we're a company, we can also spend time focusing on ensuring the software is robust, well validated, and also easy to use. Okay, so we just focus in on ultimate or collapse analysis. The reason we came into the field, albeit quite a number of years ago now, was because existing tools we felt were not serving the market well enough. There's two basic types of tool. One, traditional hand calculation type tool at one extreme, and at the other extreme we have very complex, sophisticated or advanced methods of analysis, typically based on finite elements, discrete elements, and those kind of techniques. We felt there was a gap between these two types of tool, and we set about filling that gap with what we consider to be mainstream analysis tools using numerical rigid plastic analysis. And what we're trying to do is get tools which are relatively simple and easy to use, yet have powerful features, such as in this particular case the ability to model constructions of arbitrary geometry, which isn't possible with simple hand calculation tools. And we could be talking about a geotechnical problem, we could be talking, as we are today, about masonry arch problems, or we could be talking about, for example, concrete slab analysis problems. So many similarities between those different application areas in terms of the numerical tools that we apply. Which brings me nicely on to the next slide, which is giving an indication of the products that LimitState has developed and markets for engineering analysis. So we have LimitState Ring, LimitState Geo, and LimitState Slab for masonry arches, geotechnical and concrete slab analysis respectively. These tools now used very widely in the UK and also in many countries worldwide. Those of you who've been keeping abreast of LimitState activities will also know we have actually ventured out into a non-civil engineering area now. We actually have a product called LimitState Form for aerospace automotive applications. In terms of customer base, we have many customers, many big names. So in the UK, AECOM, Amy, Arrow, Patkins, Balfour Beatty, big names using the software. Okay, enough of that. Let's move on to the main topic of the webinar today, Masonry Arch Bridges, the basics. I'll start, as I often do, by first of all just reminding everybody how many Masonry Arch Bridges we have in the world. Probably we have about 1 million spans. In the UK we probably have of the order of 70,000 spans. Rural roads, railways, we have a huge proportion of our bridge infrastructure formed using Masonry Arch Bridges. Typically we're talking about structures which are well over 100 years old, and they need to be assessed to ensure that they're safe and capable for carrying current and envisaged loads. In terms of the basic principles on which they operate from a sort of engineering perspective, we can consider them to be an assemblage of components. So we have an arch barrel which supports soil backfill material, and that provides a level road or rail surface. Often we'll focus on the arch barrel and we'll neglect the backfill, or we'll treat it as a peripheral element. It is actually a very important element, but nevertheless, looking at the arch barrel in isolation does help us understand some of the fundamental principles that are applicable in the case of a masonry arch bridge. And the most fundamental principle, I guess you could say, was discovered in 1675 by Robert Hooke. He said that as hangs a weightless cable, so but inverted stands the masonry arch. What did he mean by that? Well, if you have a weightless cable, in this case shown in red, you then suspend all the masonry blocks or voussoirs that you're going to use to form your masonry arch from that cable. You freeze the profile and you invert it, and then you build your masonry arch using those same blocks, and you find that you can fit that profile entirely within the thickness of the masonry. Then Hooke was telling us that your masonry arch will be stable, it will stand, which is a major finding, and it allowed people in the future, subsequently, once communication channels were sufficiently well developed, to actually design much more efficient masonry arch structures. Okay, so this red line is now called the line of thrust or line of compression, and one thing we can observe is that there are other possible lines of thrust that fit within the masonry. We're dealing with a statically indeterminate structure, so we don't actually know which is the current line of thrust in our structure unless we have, for example, cracks in our masonry giving us clues. However, what we do know is that when we apply, for example, an eccentric load to our arch, and we continue to increase that load, we will get to a point where we can only just fit that red line of thrust within the thickness of the masonry. So that's our limiting line of thrust, and beyond which we will get hinges forming and we will get collapse. So what I'm saying is that prior to collapse we have uncertainty about exactly how the loads are being transmitted within our structure. At collapse, things become rather more simple, and we can identify what's going on and also what the load is required to cause collapse. Other things to say is this theory of Hooke is telling us that the shape of the arch in relation to the pattern of loading is very important. It's that governs stability. So from a bridge assessment point of view, that's telling us that we need to measure the shape of the arch carefully, and if possible, use real loading patterns when we're assessing bridges, or if not real loading patterns, then certainly representative loading patterns. Other issues already touched on: surrounding fill material helps provide additional reserves of strength. It pre-stresses the masonry in effect, so the vertical dead weight will do that. Also, it will spread the load through the fill material, and also it will provide the material will provide restraint to the arch barrel as it tries to sway into itself. Currently, most modern methods of analysis focus on the ultimate limit state, partly for the reasons that I've outlined. It's much simpler in general to do an analysis of the ultimate limit state than it is of the state of the structure prior to the ultimate limit state. However, there's been quite a lot of work on this topic in the last few years, and actually with my University of Sheffield hat on, we'll be making some announcements on that in the coming months on how we potentially can apply similar techniques to provide information about what's going on prior to the ultimate limit state. So just to sum up the methods available for assessment engineers: 3 main types of tool, if you like. There's at a very simple end, there's tools such as the MEXI method, which boils down to a simple nomogram where we can effectively read off an axial load if we know various features of the geometry, right over to more complex advanced analysis tools. And in the middle we have limit analysis tools such as LimitState ring, which we'll obviously be talking about today. Okay, so moving then on to how we perform a bridge analysis using LimitState ring, and also just say a few words about LimitState ring. Why is it, how is it different? What's different about it compared with other tools? Key differentiator is that we're using a mathematical formulation which is not used in other tools. It allows us to identify failure mechanisms which are not found using conventional tools. So failure mechanisms, for example, which involve sliding, failure mechanisms, multiple hinges and sliding releases in combination, etc. Second thing is we've validated the software against high quality test results. And thirdly, we've developed a user interface which allows the users of software to use it in 2 real ways. One is in a very simple and easy way to rapidly estimate the capacity of a bridge with minimal knowledge of the structure, and in a second way to perform a much more detailed analysis using local properties when those are available. And so quick assessment approach uses a wizard, and rather than show slides, I will actually just start the software and I'll show you exactly what I mean. So when we start the software, what we can do is use this new bridge wizard, which allows us to basically step through the process of setting up a model in a very simple and easy way. So first pane requests details of the bridge. I'm just going to skip that. I'll move on to the geometry. We're invited first of all to specify details of the abutments if we want to model those explicitly. However, typically we don't want to do that, and we can move straight on to the span information. The span information allows us to specify the shape, whether that be segmental, pointed, or user-defined, etc., and also how the arch barrel is constructed, whether that's stone, bonded brick, or multi-ring brick. And obviously I can specify the details in this table here. What I'm going to do is just model a multi-span, so I click the little checkbox saying insert span after this, move on to the pier dialog. What I'm going to do is perhaps make the pier a little bit higher than we've got at the moment and perhaps put in more blocks. Number of blocks, generally speaking, doesn't need to represent exactly the number of blocks you have in a structure, but the more blocks you have, the more accurate the solution is likely to be. I move on. The second span by default will exactly replicate the first span, and I could add another pier if I wanted, another span, and again now this is replicating the data that I entered for the previous pier. So the height is already 3,000 millimeters. And I can move on. I could add extra spans if I wanted to, or leave it as it is. I think I'll leave it as it is. 3 spans is probably enough. Not bother about the right abutment. Fill profile, you can enter as many points as you have available in order to properly represent the location of the road or rail surface relative to the underlying masonry art structure. Move on to the next section, which is partial factors. Now by default these values are all unity. However, if you're working with a particular assessment code, you can easily enter the applicable partial factors. And actually the example that I'm going to show a little bit later has partial factors that are used by the UK highways authorities. So I'll just skip over that for now. I'll leave them all as unity. On to the next section, which is materials. I can enter properties of the materials. First, the masonry. I can enter the unit weight and also whether I want to model crushing or compressive, finite compressive strength for the masonry. I can also enter coefficients of friction for modeling sliding failures. For the backfill, I'm invited to enter the basic properties associated with the backfill, so the basic geotechnical properties, that's unit weight, angle of friction and cohesion. I'm also asked whether I want to model the anticipated effects of the fill, i.e. to disperse the live load and to restrain movement of the arch barrel via passive pressures. And so by default I'll leave those as checked. Move on to the surface fill. I can actually enter different properties. So for example, if you've got very different material close to the surface, large amounts of tarmacadam or whatever it might be, we can actually put in different properties and different angle of dispersion of the load. Okay, so I'll move on finally then to the load section. I can choose from a database of vehicles, or what I'm going to do in this particular case is just use a single axle, and that means that whatever number I get out of my analysis, because I have no partial factors, will simply be a multiplier on this axle load, which is 1 kilonewton, and will actually give me the load required to cause collapse in kilonewtons. If I click finish, I end up then with my bridge and my axle, and if I click the green solve button at the top, I will actually get a mechanism of collapse which is predicted. And also if you look at the output pane, I will actually get a number which is described as an adequacy factor, and here we've got a number 355. Now normally you would use vehicle loads rather than a notional 1 kilonewton load, and you'd also put partial factors in. So normally this number would be ideally somewhat above 1. Here, because we've worked with a 1 kilonewton load, we've actually got a much bigger multiplier, which, as I mentioned earlier, reflects the load required to cause collapse. And what I can do is I can move the load around and explore different failure modes. What I can also do, and I'll just show an example of this, is I can locally change properties. So for example, if this bridge was over a stream, what I could do is specify some mortar loss, and let's suppose I have 100 millimeters mortar loss on both sides. Got erosion. I can solve again, and what I see is that the adequacy factor, or the collapse load in this particular case, has gone from 351 kilonewtons down to 321 kilonewtons. So we can very, very easily with the software also look at the effects of localized details or localized defects in this particular case. Okay, what I'm going to do now is just go back to the slides and just pick up where I left off, because that second operation that I carried out, putting in the mortar loss, is an example of using the software in a more detailed assessment mode, where we're using knowledge, typically from an inspection of the structure, to allow us to refine the analysis. And here you can see how the mortar loss has influenced the mode of response. Anyway, so I've whizzed through starting up the software and starting to get some results from it. But how does it work? Well, the axial load on the road or rail surface is dispersed through the fill, and then it hits the masonry blocks. Those masonry blocks are separated by contacts where we can have crushing, sliding or hinging behaviors. Arch movement is restrained by self-weight and also by passive restraint, which in this software is modeled via what we've called backfill elements. So when these backfill elements are mobilized, they show as blue. When they're not mobilized, they show as gray. So in other words, they're mobilized if the arch moves into them, and there's no pressure exerted if the arch is moving away from them. And here we can see the main objects used in the software shown on screen. So hinges in red, a thrust line in blue, etc. Okay, so just bear with me for a second. Apologies, I've got a slide with equations on it, but really the main thing to think about is the concepts involved. What we're doing here is, for every block, such as a block in the pier of a multi-span arch, we're enforcing equilibrium requirements. So equilibrium in the X, Y and rotational sense. What are the forces involved? Well, there's certainly a self-weight force because we've got a block with self-weight, but we also have forces at the contacts. So we have stress resultants, a normal force, a shear force and a moment at each and every contact. Now, what we also need to do then is impose what we term a yield constraint on these contact forces. And the top yield constraint that we can see here in the elliptical region is actually a shear constraint. So actually the second one is a shear constraint. The top one is actually a rocking constraint. In this particular case, for simplicity, assuming that we have infinite crushing resistance. But the key thing is here we have linear constraints, and what we're trying to do is find the maximum load factor satisfying these linear constraints. Boils down to a linear optimization problem which is easy to solve. And what it means is that we get the internal forces within the structure, so the thrust line, and also simultaneously we will get the collapse mechanism as well. To be sure that the software is doing what we think it should do, as I mentioned earlier, we have validated the software against lots of experimental results carried out over the last well, 25 years or so, I guess. Here's one of the older bridges from the 1990s, getting ready for testing. It's actually a multi-ring brickwork arch bridge, subject to a load at the 3/4 span point. Here's another bridge of the similar vintage. It's a multi-span bridge. And then more recently, we've moved to more controlled tests where we've constructed a masonry arch barrel in effectively a large fish tank, and then put backfill on top of the arch, and because we have transparent windows, we can actually watch how the soil fill material and the arch barrel interact with each other, and that helps us understand how the arch barrel and the soil interaction works. Also, smaller scale, and this is a very, very small scale series of tests that's actually described in a paper in the Institution of Civil Engineers Bridge Engineering Journal in 2012. Here we were trying to isolate the different contributions of the backfill to the load carrying capacity, and what we found was that we got very good correlation with ring. So we didn't actually modify ring following this work. The work simply provided additional confirmation that the software was giving reasonably accurate results. Okay, so that's a bit of background. I'll move on then to have a look at applying the software to a highway bridge example. This is a slide showing details of the bridge. You can see it's a very, very modest structure, 2.7 meter span arches, and a relatively short, fat central pier. Actually, the diagram doesn't fully show the real profile of the structure, which is actually slightly misshapen, but you get an idea of the type of structure we're dealing with. What I would say is that it's modest structures such as the one you can see here on screen, which very often cause the most headaches, and that's basically because the foreseeable vehicle loading is likely to be quite high in relation to the self-weight of the structure. So in other words, very often you don't have huge reserves of strength when you're dealing with structures of this kind. In terms of material, this is zooming in on the bridge. So it's red clay bricks, very common in certain parts of the UK. You can also see the arch barrel is made up of two separate rings, which are separated by a mortar joint. Now, what you do in terms of analysis would depend to some extent on whether the bond between these two arch rings has become separated or become cracked or not. What I've got is a model of the structure which takes account of the real shape of the arches. So if I go to the geometry tab, what I can see is I've actually used a user-defined brackets interpolated shape, and I've entered a series of points for span 1, and similarly I've entered a different series of points for span 2. You can also see ring thickness here, 220. So what I can do again is I can click the green play button to solve the problem, and depending on where the load is applied, I will get a different failure mechanism. We now have an adequacy factor which is close to 1, and that's because if I look at the partial factors, I now have applied partial factors of 1.9 for the axial load and 1.8 for a dynamic load. And also, if I go to the loads data, I can see that I have actually got a 11.5 ton single axle vehicle on my bridge, which is exerting force of 112 kilonewtons. So that means that when I solve the problem, I now have effectively an over design factor, or an adequacy factor as we call it in the context of assessment. So this is basically telling me that my specified loading is safe, and the bridge can carry this load. However, I've only just applied this load at one particular location. Because it's a bridge, I can apply the load at different locations, and it might be convenient to actually simply traverse the vehicle across the bridge. So what I can do is I can, for example, at 200mm increments, just simply traverse the vehicle across the bridge. So we've got 30 load cases, and if we now look at that, we've actually got a series of load cases set up. But now if I click solve, then basically the program will crank very quickly through those load cases, and it will find the critical one. And actually it's indicating that the critical load case is load case 27 when the axle is near the right hand side of the structure. So that's an easier way of finding the critical load case. I mentioned the issue of multi-ring arches and the potential for delamination. With LimitState ring, it's very straightforward to look at worst case scenario here, assuming that it's a multi-ring arch and those two rings in this case have become debonded. I can simply enter the details. So instead of 210mm thickness span 1, I've got two 110mm thick arch rings. I'll do the same for arch 2, and we can repeat the process that we did before. So again, click solve, and you can see now it's going through those load cases. It takes slightly longer to do. It's done it now though, because it's computationally a more challenging problem. It's now telling me that actually load case 26 is critical, and we have a much lower minimum adequacy factor, in this case 0.53. So what I can do is, if I'm in the UK, is I can compare that with what the Highways Agency or Highways England document tells me. So if I go to the LimitState website, I can, just give me a second, I'll just pull it over onto screen. If I go to documentation, then practical assessment of highway bridges, then actually I can see that if I have an adequacy factor on an 11.5 ton single axle of 0.47 or above, then that corresponds to a gross vehicle weight of 7.5 tons. So if this multi-ring behaviour was found in practice, then clearly I would be very, very keen to consider a weight restriction on this bridge. Okay, so then just returning finally to the presentation, wrap up. So conclusions: shape of the arch in relation to pattern of loading is very important in masonry arch bridge analysis. So you need to bear that in mind when measuring the geometry of your structure, and also working out what the foreseeable loads applied to that structure are likely to be. LimitState ring, as you hopefully seen, is powerful yet relatively simple tool which automatically identifies lots and lots of failure mechanisms, sliding failure, multi-ring failure, and so forth. And two ways in which we can use the software: one, using default parameters, and secondly, if we have more information, then we can incorporate details of the real structure into the model. Okay, so I'm just having a look at the console to see if we have any questions. So I can see that we do have some questions. First question is, are your products all 2D analysis software? So in terms of a LimitState ring, LimitState Geo, and LimitState slab, they are all effectively two-dimensional tools. We can idealize in the case of LimitState ring, for example, the arch barrel in the third dimension. So we can, for example, in order to determine the effective width, but it is fundamentally a two-dimensional analysis tool. Got a number of questions from one of the delegates. Where can I find appropriate material properties, sliding friction coefficients? Material properties, sliding friction coefficients, then assessment codes are a good place to look, or alternatively, obviously design codes, although design codes, generally speaking, would suggest quite conservative values, for example, for the friction coefficient. Have your test methods included dynamic loading? Can you comment on the effect of dynamic factor of 1.8 used in masonry arch bridges? So actually in the last few years we've undertaken a large number of cyclic load tests on the arch in the fish tank that I showed at the University of Salford. Dynamic factor of 1.8 I think is questionable. I think it's largely there as described in the annex to one of the UK Highways Agency documents to allow the analysis results to correlate with test results that were carried out in the 1980s and 1990s. I think probably that will be the subject of a whole new webinar, so I probably need to move on. If arches are symmetrical, why didn't load case 6 minus not equal load case 27? Okay, in this particular case, the arch is not symmetrical. So if we look at the front of it, I don't know if you can see. It's not symmetrical. If we go to the geometry, so you've got 9 points for span 1. We're actually defining span 2 with 8 points, so it's different. So we wouldn't expect necessarily the results to be exactly the same whether we alert to the left or to the right. The other thing to say is, because this is numerical software, we will always find a critical solution. So it might be that if we had to define this symmetrically, that lowercase 6 and lowercase 27, for example, might have given exactly the same results. It would still show one of those as being critical. How do fill elements work when mobilized? So what I'm going to do is I'll just get rid of most of these load cases just to make sure it's this analysis solves more quickly. If I, for example, load the arch here, actually I'll just get rid of the 3D-ness. Oops. Front. What we can see is that we have blue backfill elements identified at the right-hand side of the structure. And what that's telling us is that the arch is moving into those backfill elements, and so we are actually mobilizing a fill force. If we click on an element, then we can actually have a look at what that fill force is and also what the fill stress is. And we can effectively, if we want to, we can compare it with that from retaining wall theory. What we typically do in masonry arch bridge analysis, we've done it for a long time, is actually scale down the full passive pressures derived from retaining wall theory in order to take account of two things. One, we have a curved retaining wall, if you like, and two, it's rotating as opposed to translating, and three, I guess, we can't afford to mobilize very large pressures because that would require large movements, and if we have large movements of the arch in the right hand side, then we would end up having gross deformations of the left hand part of the arch, and that would significantly reduce the capacity. So we try to effectively mobilize only a proportion of the full passive pressure when we're doing an arch analysis. Okay, just got one last question. Apologies for the fact that I'm not able to answer all the questions, but can backing be included? Yes, we can add backing. So if I go in here, say for the right, above the right abutment, I can put in a backing height of, say, I don't know, 500. And if I see that we've got backing elements there, and I solve again, and you can see that actually it's increased, in this case, the adequacy factor from just below 1 to just above 1 in this particular case. Okay, so I'm just going to hand back now to Tom Pritchard, who's just going to wrap things up.
Thanks, Matthew, and thanks to everybody for listening. So we're now near to the end of the webinar, and we do hope you found it informative and got something from it. For people who are current users of the software, if the webinar's prompted any questions, then please do get in touch with us via telephone or on support@LimitState.com, and we'll try and answer any questions that you may have. For those of you who aren't current users of LimitState Ring, we'll just get in touch with you over the next few days with a link to the video and see if you've got any feedback, find out if you have any further questions again. Everyone here may also be interested to know that there's going to be some forthcoming webinars dealing with other LimitState products, and please keep an eye out on our website at www.limitstate.com/events for those, and we'll also send out emails in advance of those. So finally, I'd like to say just thank you all for listening, and I hope that you can join us again for one of our future sessions. Goodbye.